Hello. In this video we're going to take a look at the postulates of quantum mechanics, and they're all going to fit on this board and they really define the whole subject. So it's taken us this many videos to get to this point because you needed a lot of background to be able to state them, but now we can state them. You should know all of them already, but let's take a look at them. The states of a system are represented by kets psi in a complex Hilbert space, which we'll call curly H. Observable quantities are represented by Hermitian operators, and we'll call them capital A with a hat on them, which are living in the Hilbert space. So if the Hilbert space is finite dimensional, these would be matrices. If it's infinite dimensional, they'll be differential operators. All such operators are assumed to possess a complete set of eigenstates. That is, the operator A acting on eigenstate A subscript n returns eigenvalue A subscript n multiplying the eigenstate. The important bit here that needs to be postulated is the fact that it forms a complete set of eigenstates. So this may not be true in the general case of complex Hilbert spaces, but it's always true in quantum mechanics. The fundamental probability postulate for measurements is as follows. The possible results of a measurement of the operator A are eigenvalues of A, an, only. After measurement of eigenvalue an, the resulting state is the eigenstate an. So something mysterious happens when we carry out this measurement, and we'll look into a bit more detail about what happens when we make measurements in another video. The probability of finding this outcome for state psi is the inner product of the eigenstate an with psi modulus squared. This is what we refer to as the Born rule. And finally, in the absence of measurement, states evolve unitarily according to the time-dependent Schrodinger equation, IH bar d psi by dt is equal to h psi of t. Let's take a look in the worked example area at what unitarily here means, but otherwise these are the postulates of quantum mechanics. Okay, so in general, a unitary operator takes the following form. We have that u dagger u is equal to the identity. So these could be matrices, and this would be the identity matrix. These could be operators, and this would be the identity operator. So the reason we require this is that we'd like our states to remain normalized at all times. So remember, all physical states in quantum mechanics are normalized. So we'd like that if we start with a state psi at time naught, this had better be normalized, so this had better equal 1. But at a later time t, this had also better remain normalized, and so this is also better equal 1. Now, for various reasons, we're aware that we should be able to write our state psi of t as some kind of operator, and we don't need to presume it's unitary just yet, which is a function of t and t naught acting on our state psi of t naught. And this condition up here tells us that since we have, so we'd like this to be equal to 1, so we'd like the Hermitian conjugate of this acting on itself to be equal to 1. And so this tells us that psi of t naught, u dagger t comma t naught, u t comma t naught, psi of t naught must equal 1. Okay, so then we know that this thing here must be the identity, because if this is the identity, then we have that psi of t naught, inner product psi of t naught, is equal to 1, but that was this condition up here. So if we start from this condition, and we require this condition as well, the only way for that to work is if this operator u is unitary. And in fact, we know what it is, because in quantum mechanics we have the time-dependent Schrodinger equation, and if you remember back, we know that psi at time t is equal to e to the minus I Hamiltonian t minus t naught over h bar psi of t naught. which fulfills this condition. So that's what we mean by a unitary operator. In fact, in general, a unitary operator can always be written as e to the I Hermitian operator, and you can check that quite straightforwardly. Okay, thank you for your time.